in reality, antennas are not isotropic, as I just mentioned, and so they do have a preference. In fact, many times we want them to have a preference. We want them to radiate in one direction and not radiate in another direction. We usually indicate that by polar plots that we call radiation patterns. So this is a normalized polar plot, and what's actually being plotted here is the radiation intensity, U, and is actually plotted in 2D. So radiation intensity U is normally a function of both theta and phi, but sometimes we will fix one angle and plot it as a two-dimensional plot. Sometimes we will do a 3D plot. It's really a matter of preference. Most plots are actually two-dimensional, and they're actually polar, like the one you see here. And they're basically normalized. So the direction of maximum radiation is the direction of 0 dB, and then we will basically normalize this down to 10 dB below, 20 dB below, 30 dB below. Besides the fact that there is a preference of radiation in this direction, in this particular graph is this direction right here, notice also that the radiation pattern includes side lobes. And notice also that the radiation patterns includes nulls. Nulls are basically directions where there is basically zero radiation. So if you were standing right at the null, you would basically get absolutely no radiation in this direction. That's a very typical radiation pattern of many antennas out there. So based on this idea, we try to capture all of this in just a single number called directivity. And of course, directivity can't capture everything you see on this graph, but can give you a numerical value of what this antenna does. So to define directivity, first we find out the total amount of power radiated everywhere. And we do that by essentially taking our radiation density and integrating it in 3 dimensions. So we capture all the power radiated everywhere. And then we divide that by the, we divide the radiation pattern with the radiation intensity rather with the amount of power that could have been radiated if this had been an isotropic radiator. So for example, in this particular case, you can see that in this direction, I have a very strong radiation, while in this direction, I have no radiation. An isotropic radiator that would have done exactly the same, would have radiated the same amount of power, would likely have a radiation graph that might have looked something like this. Right? So if I have defined basically directivity, let's say along the x-axis here, clearly the isotropic radiator would have radiated a lot more than this antenna that's giving me 0. While if I define directivity in the maximum direction, my antenna does a lot better than the isotropic radiator would have done. So typically, we will define our maximum directivity, which is defined at the direction of maximum radiation. And we will basically do this calculation and essentially give you a number. So for example, if the directivity is, let's say, 3, and it will actually be a unitless number, it means that in this direction, this antenna gives you 3 times as much power density than an isotropic radiator would have given you. What is really important to understand here is that there is no actual gain in the sense of an amplification. The antenna itself doesn't amplify its input power. It simply focuses on the right direction. So it's almost like a balloon. You squeeze a balloon on one dimension, on one direction, it basically bursts out in the other direction. That's exactly what we want from antennas. There is no active amplification. It's literally a piece of metal with dielectric. But there is definitely a directionality involved here, which we try to capture through this definition of directivity. So here's some typical directivities for some antennas that you may know or may not know. So a short dipole antenna is a very common antenna. Its directivity is barely above 1, is 1.5, or in dBs is 1.76. The patch antenna that you saw before has a directivity typically between 3 and 6, or in dBs between 5 and 8. Some of the dish antennas, the satellite dish antennas you will see out there, will actually have directivities in the order of many thousands. Or in dBs, they will actually reach 30 or 40 dB out there. And we will see some examples later on. Now, a little bit more important, or to be honest, far more important than directivity, is actually the gain of an antenna. So the gain of an antenna is nothing else but a multiplication of the directivity of the antenna, which again is a property that depends only on which direction I radiate more or less, and the efficiency of the antenna. Now, the efficiency of the antenna, which is shown here as eta, is essentially telling you how much of the input power you're actually radiating. So if I'm putting basically an input power of 1 watt, but I'm radiating at 0.8 watts, then essentially my efficiency will be 80%. And that's actually pretty good. But there are some antennas, like for example the short dipole antenna, that may have a gain of only, an efficiency of only 1%. If your efficiency is only 1%, that means that maybe only 10 milliwatts will get out with the 1 watt. And that's quite bad, because even if your directivity is pretty high, at the end of the day, the receiver cares about the gain and not about the directivity. So I would say directivity is a definition for kids. Gain is a definition for adults. So keep in mind that gain is what we care about and not directivity, meaning we want both high efficiency and we want preference radiation for something to be useful.